Hi everyone. In this video, I want to give a summary of how the things we've learned recently can help us with our goal of anti-differentiating rational functions. To start with, let's remind ourselves of an important fact. With rational functions, it's always possible to find a partial fractions decomposition, and that means every rational function can be anti-differentiated, provided we can find antiderivatives of partial fractions. And we know there's only two types of partial fractions. First, there's the constant over linear type, and there's also the linear over irreducible quadratic type. When it comes to finding the antiderivatives of these, the constant over linear type can always be approached by letting u equal the linear function. And that's because the derivative of a linear function is always a constant, so there will never be any complications when you're calculating du. And so with that, what you always end up with really is an integral of u to the minus k, which is pretty straightforward from there. So from that point of view, I'd say these types of antiderivatives are relatively easy. These other types, though, are hard in general. Back when we learned partial fractions, I mentioned that these require us to study inverse exponential and trig functions. And now that we've done that, our current knowledge allows us to do these types of integrals, at least in the case where k equals 1. And that's what I hope to convince you of in this video. The case where k is bigger than 1 is still out of reach, but we'll get there eventually. But if this is making sense so far, let me show you how to approach the k equals 1 case. There are two important things I've suggested you always be looking out for when finding antiderivatives. One of those things is the structure of f prime over f, and the other is sums and differences of squares. We've seen that the f prime over f integral suggests the antiderivative becomes a logarithm, and the sum and difference of squares suggests using one of the inverse trig formulas, either arcsine, arctan, or arcsecant. It turns out that every single one of these linear over irreducible quadratic integrals can be solved using just these two ingredients. But just to reiterate, I'm only talking about the k equals 1 case here. Let's do a few examples to convince ourselves of what I've just said. Anytime you encounter a linear over irreducible quadratic integral, the very first thing you should do is check if it can be made into the form f prime over f, because that would really represent the easiest case scenario. So let's think about the derivative of the denominator. In this case, that derivative is 6x minus 4. So this is the numerator we wish we had. Unfortunately, the numerator we actually have is 3x minus 2. But actually that's not too bad because 6x minus 4 is just double 3x minus 2. So we could get the numerator we want if we just multiply by 2 up here. But if I do that, then I also need to divide by 2 to cancel out the change that I just made. After expanding, we do then see a numerator of 6x minus 4, which is what we wanted. So this now really is of the form f prime over f. And anytime we see that, we know the result is the natural log of the denominator with an absolute value. And that's it for this problem. Let's try another one. We see a linear over irreducible quadratic. So my first question is whether this can be written as f prime over f. Unfortunately, in this case, that's not possible. Pause and convince yourself of that if necessary. But this is why we have two things to look out for. When the f prime over f approach fails, we can always look for sums and differences of squares instead. There doesn't appear to be one in the question given to us, but remember that any quadratic expression can be viewed as a sum or difference of squares in disguise. We just need to complete the square to get what we want here. So as always, we begin by grouping the first two terms in a set of brackets. Then we identify the coefficient of x, which is negative 2 in this case, and we always divide that coefficient by 2 and then square the result. In this case, doing that gives us a value of positive 1, and so we add positive 1 inside our brackets, then also subtract 1 outside the brackets to cancel out the change we just made. Outside the brackets, 3 minus 1 can simplify to plus 2, and the expression inside the brackets can factor into a perfect square. And with that, we're done completing the square. Now we can see this shaping up to look like the arctan integral by thinking of the denominator as u squared plus a squared. However, thinking of it this way requires us to perform a substitution properly. So we let u equal x minus 1, in which case we can see du equals dx, so it's safe to put a du directly where we had a dx previously. And now this matches the form of the arctan integral, where a equals the square root of 2, so we can directly make use of that formula and come up with our answer. And with that, you're done. Just don't forget to express this answer in terms of x rather than u. So far, we've only looked at examples where we need to use either f prime over f or a sum of squares, but some examples need us to make use of both of these ingredients. For the example we see here, the f prime over f structure could be seen if all we had in the numerator was a 2x. But unfortunately, there's also the minus 3 up there that we need to deal with. So if we could separate the 2x from the minus 3, that would give me a good place to start with this problem. So that motivates me to break up this fraction. To do that, I can form one term that has a numerator of 2x, which is really what I wanted, and then another term that has a numerator of negative 3. Now, the first term really does have the form f prime over f, so we know that one will be the natural log of the denominator with an absolute value. The second term is not of the form f prime over f, so we should expect to use a sum of squares to figure that part out. And in fact, you'll notice this term does resemble arctan of x, but for that we want a 1 in the numerator rather than this 3. No problem. We can always pull this constant in front and end up with something that does exactly match our arctan formula. So we can declare this remaining part as arctan of x, and we're finished this problem. I think for the moment I've given you enough to think about, so I'll see you in the next video where we'll look at some more complicated examples of the linear over irreducible quadratic.